thank you for the absolutely lovely introduction. So I did give a version of this talk. It's changed quite a bit between then and now in Porto last year. So thank you so much for coming to this talk slot. As Adele said, my name is Jodie Burchell, and I'm currently working as a developer advocate in JetBrains, all nicely branded today. I've been a data scientist for almost 10 years, and a big chunk of my career I actually spent in NLP. Kind of a funny story about that. One of the jobs that I worked at in NLP, when I left, we were starting to work with early large language models like BERT. And I have friends who are still working there, and one of them reached out to me a couple of months ago and said, the CEO's been in contact with our team, and he wanted to know what we're doing about working with AI. And he's like, dude, we've been doing that for the last 7 years. So confusion abounds. So prior to my career as a data scientist, I actually did my PhD in psychology. So you can imagine that I've been watching this space with a lot of interest, but I've also been watching it with a lot of concern. And one of the biggest areas where I've sort of been having concern is about the messaging around large language models. So what I want to do in this talk is take a much more measured look at this at this area, and cut through the hype a bit. So for the past 2 years, no big surprise, we've been in a full-on AI hype cycle. I'm actually surprised you came to my talk about LLMs because I'm quite sure everyone's sick of hearing about them at this point. So we've had claims that range from models like Lambda showing sentience, to speculation that huge swathes of the white-collar job market are going to be replaced by generative models, to even doomsday claims that we have an AI apocalypse on the horizon. So it's been an absolutely overwhelming flood of opinions, idea, and speculation. So naturally, for most people, it's really hard to know what to think about these models. Are they actually useful? Or are they just fun toys? Are they just a gimmick? What can we realistically use them for? And are they really going to replace or destroy us? So what we're going to be doing over the next 40 minutes is cutting through the hype and looking at the actual applications and limitations of these models. We're going to see the context and the science behind these models, and we're going to challenge some of the more outrageous claims, such as we're on the path to artificial general intelligence or AGI with these models. And obviously, with a 40 to 50-minute time slot, I've had to leave out a lot. I think we should have a few minutes for questions at the end, so please do send them through the app or come and find me afterwards. So for a lot of people, models like ChatGPT 3.5 and 4 felt like they came out of nowhere. But naturally, they're part of a long history of research in this field, specifically in the area that I mentioned of natural language processing. So the interesting thing about these models is that the generation of text was not the original aim of earlier models in this field. It was to build models that could automate tasks with text that require huge amounts of manual labor, things like text classification or summarization. So let's have a look at how this journey evolved. So large language models all belong to a type of model called neural nets. And these were originally proposed as a way of artificially mimicking the human brain. So research in this area started in the 1940s and went in stops and starts up until sort of the 1980s, where a number of important technological limitations were overcome. However, the practical application of neural nets was limited, even up to the start of the 21st century. And this is because these models have really intense computing power requirements. So researchers found the larger they made these models, the more they can learn about their input data, and the more accurate or sophisticated their predictions can be. But this requires the use of processing units that are really efficient at doing huge amounts of matrix multiplication. Hence you hear all this mention of linear algebra in this area. So this leads us to our first breakthrough on the path to large language models, which was the development of CUDA. So CUDA allowed us to transform GPUs into all-purpose matrix multiplication machines and therefore make the training of large neural nets much more feasible. As you increase the size of neural nets, they also become, unsurprisingly, much more data hungry. So therefore, the next big advancement was the development of a data set called Common Crawl. This is a huge dump of frequently linked pages on the internet. And the development of Common Crawl meant that researchers now had sufficient text data to start training more and more complex language models. And the final step was innovations on the modeling side. So despite early predictions that this would be an easy problem, working with text turned out to be quite complicated, even with all of this nice computing power and all of this data that we now had. So language is really complex and it's highly context dependent. So it took some time to develop a type of neural net that could actually capture these sort of relationships between words. And this also happened in 2007, the same year that Common Crawl was developed, with the development of a type of neural net called long short-term memory networks, or LSTMs. We're not amazing at naming things in this area, you may have noticed that, not a very catchy name. So these models were one of the first to really understand words in their context sentences. And therefore, they were able to vastly outperform previous models on a range of tasks. So of course, they were better at text generation than previous models, but they were also one of the first general purpose natural language processing models. They were capable of doing a range of tasks like text classification, summarization, and translation. And in fact, you may have noticed that Google Translate suddenly got a lot better in 2016. This is because we started using LSTMs under the hood. However, a major limitation of LSTMs is that they're forced to process words in a piece of text sequentially. So what they do is they process the first word, they remember something about it, they process the second word, they add that information to this memory, and so on and so forth. So this caused a number of problems, but the biggest of these is it led to problems with scaling these models, limiting how big researchers could feasibly make them. So the models that solve this are, of course, transformer models. You would have heard this term everywhere. This type of model avoids this sequential processing and therefore allows models to get really huge. And a really cool thing about transformer models is as part of their training, they learn really rich internal representations of how language works, and therefore they're of course generalist models. They're able to do a range of NLP tasks that they were not explicitly trained to do. So this has kicked off the current generation of text processing models, and this is why we can have the large in large language models. So the branch of transformer models that evolved into generative or autoregressive models are the generative pre-trained transformers, or GPTs. And the first of these came out in 2018. So GPTs have been a very successful type of model, and pretty much every single one of the many large language models released in the last 3 years have a GPT-based architecture, including heavy hitters that you would have heard of, like ChatGPT, GPT-4, Falcon, Mistral 7B, Gemini, and Claude. So now that we have an understanding of the recent history of large language models and some of the foundations that they're built on, let's have a closer look at the GPT models. So we're obviously not going to look at every variant I just showed you. We'd be here for the rest of the talk doing that. But what we're going to do is have a look at the group of models developed by OpenAI, because they were the ones who came up with the first GPT model. So one of the most interesting problems for natural language processing is machine translation. And this was the first major use case for transformer models. So in order to do translation between two languages, transformer-based model needs two components, an encoder and a decoder. So the role of the encoder is to learn everything it can about the source language and send that information over to the decoder. Now the decoder's job is a bit more complex. It needs to learn everything it can about how the target language functions, but then it also needs to use that information sent over by the encoder and try to predict word by word the most likely matching sequence in the target language. So you can see that in this example here. Let's say we have the sentence, I have visited Italy in English, and we want to translate it to German. So our encoder will have learned a whole bunch about how the English language functions, and our decoder will have learned a whole bunch about how German functions. So our sentence is first processed by the encoder, and then word by word, the decoder will generate the most likely matching sequence in German. However, something that researchers quickly realized is that decoder units all on their own are pretty useful. So as we discussed, a decoder's whole job is to learn the ins and outs of how a target language works and use that knowledge to predict the next word in a sequence based on an input. So researchers started to think, well, what if we cut out this source language, we cut out the encoder, and we just trained decoders by asking them to predict the next word in the same language? what we can do is train these models by showing them millions of words in the same language and get them to adjust their predictions based on whether they can successfully predict the next word or not. And we then end up with, as a result, with a model that has a pretty good idea of the next most likely words to come in based on a given text input. So we can see that with this example here. We have the two words as an input, I have, and the model has learned the probability of the next word, and the next word after that, and so on and so forth. Now, interestingly, this was initially not a huge breakthrough because of its ability to generate text, but because it solved the problem of where to get enough data to train these really huge models. As I said, the bigger you make neural nets, the more data hungry they get. So the problem with training most models, this is machine learning models across the board, it's not unique to LLMs, is you often need to manually prepare the data in some way. It might be labeling data or pairing things up, for example. And obviously, if you want to make really, really, really huge data sets, this gets really costly or potentially unfeasible. But this problem is solved if you're basically using a sentence as both the input and the output. You just need to cut the sentence at a point, use the beginning of the sentence as your input, and you use the next word as your target. And this gives you a ready-made training set which scales very easily. So this was the basis of the GPT models, and along with that beautiful scalable transformer architecture is the secret of how these models have been able to grow so big. So the way these models work is they roughly increase their size by stacking decoder units. It's not exactly how they work, but this is the general idea. And what this does is it increases the number of model parameters. So this is the size of the models. So the first GPT was 120 million parameters, which seems quaint at this point. The second was 13 times that size at 1.5 billion parameters. And you can see the models have just kept growing and growing up to GPT-4, which is estimated to be at around a trillion parameters. And I left GPT-4 out. I just can't keep up with all this stuff. So I was like, you're staying off this slide. So the models have grown over successive generations to be better and better at a range of natural language tasks. And we can get a sense of how the models have evolved by seeing how they each respond to the same prompt. Complete this sentence, Belgium is. Apologies to any Belgians in the audience. I'm not taking the piss, but this is just the one I've been using for about a year. So GPT-1 is really good at generating text which is grammatically correct, but there's no real sense of context. So this is what GPT-1 came up with for our prompt, which the best you can say about it is it's grammatically correct. Now, GPT-2 is a bit more polished than GPT-1, but it still tends to come up with really weird outputs. So here is GPT-2's attempt. So GPT-3 is where the models start learning not only grammar, but they start encoding some information about the words that they're trained on. So here's GPT-3's attempt. It gives us a nice little sentence, which not only makes sense, but it actually gives us on-topic information. And then finally, when I put this into ChatGPT 3.5, it wrote a whole bloody essay. I had to cut it off, but it kept going on about multilingualism and comic books. It would have gone on forever. So now we know where LLMs have come from, and we've explored how they work under the hood a bit. Let's turn to how these models are being perceived in both the tech world and beyond. So as we've discussed, these models now exist in a hype cycle, which makes claims about them that goes far beyond their original purpose as generalist natural language processing models. And the most sensationalized of these claims, as I said at the beginning, is that LLMs are showing signs of artificial general intelligence, or AGI. So these claims of AGI have run the gamut, and they've been backed up actually by some of the most respected researchers in the field, like Geoffrey Hinton, one of the so-called three godfathers of AI, or backed up by papers from Microsoft Research. So with all these people throwing their weight behind the idea of LLMs showing AGI, how can we be sure that these models haven't developed intelligence? So let's go back to May of 1997, when then world chess champion Garry Kasparov was playing Deep Blue, IBM's chess playing AI. And this was the second time that they'd faced each other. So in the second game of the match, Deep Blue made an unexpected move. And this rattled Kasparov, and it made him believe that the model was far more sophisticated or advanced than it actually was. So thrown off his game, he actually ended up losing this game. Then he lost the third. Then he lost the fourth. He lost the whole match. And the press went crazy, speculating that if we could solve chess with artificial systems, then surely AGI was just around the corner. But as you can see from this incredible quality of this screen capture, that was almost 30 years ago, and we can see how those predictions panned out. The problem with trying to assess intelligence in this manner is that it confuses the output of an AI system with the mechanism that the system took to get there. So we can use these skill-based assessments in humans because we know that in humans, the ability to demonstrate significant skill in an area is reflective of an underlying raw general ability. Machine learning or AI models, they don't work this way. They try to optimize for their training goals, and if they can take shortcuts to get to good performance on those goals, they absolutely will. The mistake is thinking that the pathway required to learn some skill for a machine learning model, including LLMs, requires the development of an underlying intelligence. This illusion of skill-based intelligence is so well known, it actually has a name, the Kaggle effect, after the well-known machine learning competition website. So on this website, people compete to create an algorithm that can best complete some sort of task. And the winning solutions are so good at doing this specific task that while they're doing it, they seem to show a sort of intelligence. But as soon as you try to get them to predict on some sort of example that's too far outside of what they were trained on, they fail. They show brittleness. And this is a problem plaguing the current assessment of intelligence in LLMs. They focus very strongly on how these models perform in specific tasks, ignoring how intelligence is actually defined and measured in humans. And this is because while researchers in these areas are very, very well established in their fields are things like computer sciences, physics, mathematics, or engineering, not psychology. So let's have a look at an example that shows why these skill-based assessments are a problem. So if you remember back to the beginning of last year, one of the biggest hype topics, especially after GPT-4 came out, was that this model was able to solve medical and law exams. And there was all these claims that this model was going to replace doctors and lawyers. And then they came for us. The model started solving leak code problems. And then they started saying these models are going to replace programmers. So let's take a closer look at this last claim. So there's really a great example circulating on Twitter around the time that GPT-4 came out. So there's this guy called Horace Hay, and he tested out GPT-4 with some coding problems from a website called Codeforces. And what made Codeforces really good for this particular little experiment is the date that each coding problem was released is actually timestamped. So what he did is he collected 10 puzzles that were released at the time that GPT-4 was being trained. So potentially could have been in their training data. And he ran them through GPT-4, and what would you know? GPT-4 got all of them right. Congrats, it's coming for our jobs. But then what he did is he collected another 10 puzzles that were released after GPT-4 was trained. These were of an equivalent level of difficulty, but this time, GPT-4 got every single one of them wrong. So what happened? Well, this raised a lot of suspicions that GPT-4 was only able to solve these puzzles because they were in the training data and had just memorized them. So another researcher, Sayesh Kapoor, tested this explicitly by asking GPT-4 about a Codeforces puzzle that was available at the time it was trained. And obligingly, GPT-4 vomited up the complete source, confirming that it did indeed have Codeforces puzzles in the training data. So I think this is a really neat example that these skill-based assessments of intelligence in LLMs can be wildly misleading. Instead, we need to look to how well these systems can solve tasks they've never seen before. That is, how well can these systems generalize? So the way this was approached by Francois Chollet, he's a very well-known AI researcher, he works at Google, he defines this in a hierarchy of generalization. So what we do is we start at an absence of generalization. This includes systems that know all of the possible outcomes in advance, such as if you've got an algorithm that can play tic-tac-toe, it will be able to play it by knowing all the possible configurations that it can play with in advance. We then move to local generalization. This is where a system can make inferences on examples it hasn't seen before, but only if those examples are similar enough to things it was trained on. And machine learning models fall under this, and this is an illustration of the Kaggle effect. Broad generalization reflects a human-level ability in a single broad activity domain. So a famous example of this is the Wozniak coffee test. This was proposed by, unsurprisingly, Steve Wozniak of Apple fame. And he proposed that if you can have a system that can go into a kitchen and can complete all the steps required to make a cup of coffee without human intervention, that would show broad generalization. And full self-driving cars would also fall under this categorization. We then have extreme generalization. This is essentially human-level intelligence. And this is basically where you have a system that can solve problems it hasn't seen before, even those that only share some abstract commonalities with things it has seen before. And it can solve problems across the scope of what you'd expect humans to be able to solve. So you might be thinking at this point, I'm focusing a lot on human-level abilities, but we're talking about artificial systems. Don't we want them to go beyond what we can do, to be better than us? And this leads to the final level, which is universality. This is the ability of a system to solve any problem in the universe, beyond even problems that have any relevance to us. The thing with universality is it shouldn't really be considered as an initial goal for an artificial system for a couple of reasons. The first is, as developers, we know that all problems need a scope in order to be useful. And the current scope we have is being able to automate tasks that we ourselves do manually for artificial systems. The second is we haven't really even been able to solve up to broad generalization. So we should maybe focus on these lower levels before we aim quite so high. So if we come back to intelligence, we can actually line up Cholet's conceptualization of generalization with the actual accepted definition of intelligence in humans. So this conceptualization says that humans have a general ability to learn, called G, or general intelligence. And we use our general intelligence to learn broad activities, such as how to cook or drive a car. And within those broad activities are tasks that we can complete, such as whisking eggs or using an indicator. And you can see that an artificial system's extreme generalization aligns with G in humans, broad abilities align with broad generalization, and specific skills align with no generalization or local generalization. So given this overlap, it seems fair that we can derive lessons from measuring intelligence in humans, which is an established field, and apply them to measuring intelligence in artificial systems. So as an aside before I go on, I want to say I am a psychologist. I am aware that intelligence is a controversial field. This is not being proposed as a silver bullet, but it's more giving us a framework to move beyond these skill-focused assessments of intelligence in these systems and try to get a sense of how well a system can truly generalize. So Cholet also proposed a method of maybe designing or building a system with artificial general intelligence. So he defines it as follows. An artificial system should be able to demonstrate the ability to solve a task. So far, so familiar. But it does this by using knowledge encoded in a skill program relevant to that task. And the skill program is generated by a human-like intelligent system. So these skill programs are refined on input about both the situations they encounter and how effective the response has been. And the intelligent system itself learns over time through exposure to more and more tasks. So Cholet also argues that if we're talking about a human-like intelligent system, we should also presume that such a system is designed with the same priors or skills that humans are innately born with. And this is elementary geometry and physics, arithmetic, and an understanding of the agency of others. So skill programs will be able to encode their experience with tasks and remember how they solved such problems in the past. And tasks themselves can vary based on generalization difficulty. So the generalization difficulty of task is quite central to this system design. It's basically how different tasks are from things that the system has already seen. So obviously tasks that are much more different, are quite different to things that the system has seen before, are going to be much harder for the system to solve, and it will need to be able to generalize more in order to successfully solve them. So what this gives us is a starting point, a conceptualization of how we might build a system with artificial general intelligence. So Cholet's work has been followed up with researchers from DeepMind. These were actually the precursor to OpenAI and were then acquired by Google. So they again start from the idea that an intelligent artificial system must be able to generalize. But they simplify this dimension by breaking it into narrow and general systems. And to this, they add a second dimension, performance. And they measure this by the percent of people that it can outperform on a particular task or range of tasks. And the way that they kind of break it up is they have a range from no people are outperformed to people unskilled in that task, to 50% of people, 90%, 99%, and then finally, all people are outperformed by that system. So let's first have a look at systems they classify as having narrow generalization. So in terms of systems that can outperform no one, they put calculators and other systems that need to be entirely manually operated. Under emerging narrow AI, they put GOFI, or good old-fashioned AI. These are these old school, I know, I love that term. These are systems, those kind of old school ones that needed to be encoded specifically with rules. And then at the higher ends, they have systems like Grammarly that can outperform 90% of people in terms of spell checking and grammar tasks. They have our old friend Deep Blue that can outperform 99% of people at chess. And then they have a system called AlphaFold that can predict a protein's 3D structure better than 100% of people, even skilled scientists. But as impressive as these are narrow systems. As we know, the true path to AGI is in systems that can generalize. So let's see what the DeepMind team puts here. Well, so far they only have 2 systems. And interestingly, they classify ChatGPT as emerging AGI. I strongly disagree with this. As I've just shown you, Cholet's definition, which is different from what these authors have put together, is that the scope of generality includes all tasks that a human would be reasonably expected to encounter. And even ChatGPT 4.0 is still limited in what it can do. The other interesting thing is that the DeepMind team were unable to find other examples on the higher ends of generalization. So what this shows is these researchers really believe that we have quite a long way to go before we get to AGI, or as they're calling it for some reason, artificial superintelligence. I guess AGI got, not sexy enough and they had to change the branding. So coupling this with Cholet's definition of how we might build such a system, I think there's really enough evidence here that we are quite a long way off this goal. So what does this mean? Does it mean that LLMs are not useful? Well, of course they are, but only when they're applied to the problem domain that they were designed to solve, which, as I've been saying all throughout this talk, is natural language problems. So we've touched a bit on what natural language tasks are throughout this talk, but let's take a step back and define what they really are. So this problem area is pretty broad, and it encompasses anything that you might want to do with natural languages. Natural languages are languages like Dutch, English, Mandarin, ones that evolve naturally. So as I mentioned at the beginning of this presentation, these are problems we've been trying to solve for decades. And LLMs are simply the latest and so far most sophisticated tool we've had to solve these problems. So let's have a look at some examples of natural language problems. This is just a taster, but it will give you an indication of what this problem domain looks like. So LLMs are good at doing the following. They're good at translating between one language and another, but only if the model has been trained on sufficient examples of both language. They're good at text classification, where they can infer the topic of a piece of text and assign it to a category. They're good at summarizing longer pieces of text into shorter ones. And they're good at answering questions, or question answering as it's called, where a model can provide an answer based on a question passed in as an input. So we're going to focus on this application for the rest of the talk. So LLMs can answer questions in a few ways. They can, of course, answer it using their parametric knowledge, as we saw with the slide about Belgium. So during training, sufficiently large LLMs will be able to encode knowledge that's contained in their training data. So depending on the model, depending on the training data, LLMs may be able to answer questions accurately based on this parametric knowledge alone. LLMs can also be further trained to better answer questions in a specific domain, and this is a technique known as fine-tuning. So the idea is you create a data set which is comprised of high-quality inputs, questions, and the expected output. and you further train the model so that it returns outputs that are more in line with this data set. And after further training on this data set, the LLM will be better equipped to answer questions in this specific domain. And then finally, there's one of the most talked about methods at the moment, which is retrieval augmented generation, or RAG. So this is where additional context relevant to the input prompt is pulled in from some source external to the LLM. And this is then incorporated into the prompt and helps the LLM more accurately answer the question. So let's focus on RAG a bit more deeply and see how a RAG pipeline might be used to answer a question. Who won the American Super Bowl this year? So I picked this question deliberately, not because I'm a huge fan of American sports, but because it's a relatively recent event. So most models are not going to be able to answer this question based on their parametric knowledge alone. So instead, they're going to have to rely on pulling in this information from somewhere else. So how can we answer this question using a RAG pipeline? Well, just like when we use an LLM normally, we create our prompt, in this case, our question about the Super Bowl. However, rather than passing this directly into the LLM, we can first gather some additional information. So this information can come from a variety of places. It could actually come from a web search engine, and if you've used ChatGPT-4, that's actually what it's doing sometimes under the hood. It's actually pinging Bing and pulling in information. But if you're dealing with sensitive documents, you're going to want to store that internally some way in some sort of database. So how do we then retrieve information from our database at question time, at the time we want to get our LLM to answer our question, and do this in a way that's efficient? Well, the first thing we need to do is divide our documents into chunks. We then feed these chunks into a second, what's called an encoder model, and as a result, we convert these chunks into document embeddings. And these are then stored in a vector database. So if you've heard things like Weaviate or Pinecone, all these vector databases people are talking about, this is why people are using them. At retrieval time, the prompt is also converted into a document embedding using that same model. And the most similar document chunks are retrieved from your vector database. So we can see for the Super Bowl query, we have two chunks. One telling us that the Kansas City Chiefs won against the San Francisco 49ers, and a second telling us the score. We can now build our augmented prompt. We instruct the LLM to ignore its parametric knowledge and only use this additional information we retrieve from our vector document database when answering the question. And then, voila, the LLM is now able to accurately answer our question. So let's now jump over to PyCharm and see how we might actually be able to build our own simple RAG pipeline for question answering. Okay, sorry, it's going to be slightly awkward. All right, so what we're going to be dealing with in this demo, if I can find my mouse. Can you see my mouse? There we are. Okay, so what we're going to be dealing with is a really large PDF which basically contains all of the PyCharm documentation. I thought this was very clever. I was doing a demo of PyCharm using PyCharm documentation, so, patting myself on the back for that. So this is a really huge PDF. It has almost 2,000 pages, and because it's not indexed in any way, it's just a plain PDF, we're actually going to have a lot of trouble actually searching through that if we want to answer questions. So we can build a question answering RAG application by ingesting this documentation and searching over it using our LLM. So how are we going to do this? We're going to do this using an open source package called LangChain. Now, LangChain is a really, really powerful application for extending the functionality of LLMs beyond just sort of simple input-output systems. And at the moment, it's only officially supported in Python and JavaScript, but because it's been such a popular package, it's been ported actually to a lot of languages in community projects. So I've seen Java, I've seen C#. So if you're interested in using this and you're not working in Python or JavaScript, you may want to have a look around for one of those community projects. Okay, so let's now go through our application. So obviously the first thing that we need to do is choose an LLM that we're going to use. So that's what we do here. I'm going to be using an OpenAI model, so we have the syntax for doing that there. Then, of course, we need to load in our gigantic documentation that we're going to search over. In my case, I'm using a PDF, but you don't need to use a PDF. LangChain supports a lot of different formats. So if you want to use some other type of text format, you can have a look through their documentation and see what they support. So now we have read in our documentation, we need to split it into chunks, just like I showed you in the previous slide. So we split that based on character, and then we have our chunks. And then we need to convert them into document embeddings and store them in the vector database. In this case, we're using a Chroma database, and we use a particular embedding model that we want to use for that. So once it's in the vector database, we need to retrieve it when we want to ask a question. So this is what we do here in this method. We create our retriever, use that on our database, and we can set different parameters like potentially the number of chunks that we want to retrieve each time we ask a question from the vector database. And then having put together all those components, it's actually really simple as you can see. All we need to do is bundle it together in a little application. So this is called a chain in LangChain, and you can see we're building a retrieval QA chain. Don't worry if you didn't get all of this. I'm going to be providing the code at the end of this talk, so you'll be able to play around with that yourself. So now that we've created our app, we need to be able to instantiate it with different parameters. And there are, as you can see, a lot of different levers that you can pull when creating RAG pipelines. So I'm not going to go through all of these. The talk would go 20 minutes over and Adele would be very angry with me. But again, you can go through this notebook at your own leisure and see the different parameters you might be able to tweak in order to optimize your own pipeline. However, the most important things I want to point out to you is the model that I've chosen to use to answer the questions. I've used ChatGPT 3.5. So I've already shown you how powerful this model is. It's going to help us get good performance on a range of natural language tasks, including question answering. And I'm also retrieving 5 chunks per question in order to answer my question. Okay, great. So we built our application. That was easy. So now we can start asking questions. So the first question I'm going to ask is, what are the options for debugging with PyCharm? And you can actually see that it gives us a really nice answer. This is the summary given by the LLM. It tells us about creating breakpoints, tells us about stepping through code, tells us about evaluating expressions, et cetera, et cetera. So if we go down here, we can actually see the chunks that our application has used to answer this question. So we can see this first one is very relevant. This second one, very relevant. But if we scroll down, the last 2 chunks are actually not that relevant. They more seem to be from overview pages that just mention debugging. And this is where you can see that trade-off you have to do with your hyperparameters. It might be that 5 chunks is too many, and there are different kind of levers you can pull in terms of that. So now that we have been able to ask one question, we might want to ask a follow-up question. We have a chat after all. So maybe we want to ask, have you left out any other types of debugging? But we need the application to understand what it's already been asked. So we can do that in a really simple way here. We can basically pass in the first question that we asked and also pass in the result that it gave us, that little answer that it talked about, breakpoints and the following. And then we assign that as one of the parameters when we invoke the application. And you can see it's given us a follow-up answer. It's now telling us about debugging in specific use cases, like JavaScript or specific Python frameworks. So to finish the demo, I want to show you something kind of wild. I was so excited when I put this together. So like I talked about, LLMs are generalist natural language models. So this means that the same model can often do multiple tasks. And one of those tasks is translation. So because I'm using a sufficiently powerful model, I can actually do queries in different languages. So German to English translation is supported by this model. So I can ask, how can you install PyCharm in German? What my application then does is it goes away and it finds me English language document chunks that are relevant to this. Sorry, I'm so excited. And so you can see this is relevant, installation guide. You can install PyCharm doing the following. And then what it gives me is a relevant summary in the original language. So I just think this is so cool. Like I said, I'm going to give you the code. Please go away and play with it yourself. But for now, I'm going to end with a boring cautionary tale, just for a couple of slides. I'm sorry, where is my mouse? There we are. Okay, so this is the point where I tell you like a boring data scientist, that after showing you this really cute little neat RAG app, working with RAG, in fact, working with LLMs in deployment is not really simple and comes with a lot of gotchas and pitfalls. So let's start with problems you might have with RAG. So do you remember all those levers I was talking about that you can pull, like the number of chunks that you return per query? Well, all of these can massively impact the performance of your RAG app. So this can include important things like the size of the chunks, how you create the document embeddings, what model you use, how you retrieve from the database, and how you create your prompt, how you integrate that information into the prompt. And then with LLMs generally, not all LLMs are suitable for all tasks. So while they are generalist models, different models may have specializations in different things. They may be trained on specific data sets. So like a really simple example is, let's say you want to use a model for some reason for translating Frisian to Dutch. Because Frisian is quite a small language, if your model has never actually been trained on Frisian text, then your LLM's just not going to be able to do this translation. It still needs the underlying data. It's not magic. It doesn't just create that information from nowhere. And if it does, it's a hallucination. So if you don't pick the right model for the task, or if you don't tune your applications correctly, this can lead to poor performance. It can lead to poor quality answers. And as I said, it can lead to hallucinations. And I guess this leaves you with the final question. How do you know whether the LLM that you want to use is going to be appropriate for your use case? Well, this gets into a really huge and complex topic, which I'm not going to have time to get into. I'm just going to touch on, which is LLM measurement. So a number of benchmarks exist for measuring how well LLMs can perform on natural language tasks generally. And you can see the performance of various models on leaderboards, like this one created by Hugging Face for open source LLMs. However, how a model will perform on your specific task is really going to depend on the domain and the use case. And potentially you may need to go and seek domain-specific benchmarks or even create your own benchmarking data set. So in conclusion, LLMs are powerful but still limited models. They're not on the brink of developing AGI, but nor are they without application and only part of an empty hype cycle. The trick is picking the right use case, carefully tuning and building your deployment, and making sure you measure your performance carefully. And if this sounds familiar, it's the same boring problems we've been dealing with in software development and machine learning for decades. Thank you very much.